All right, let's look at the differences in critical state behavior of sand and clays. There are some differences that we need to keep in mind with respect to the shape of the critical state line in E natural log P prime space. So let's look at some of these differences. The first difference is that the density of sand here is really controlled by depositional energy. If you want to make sand dense, you do some compaction. You densify the particles by imposing vibration on it or doing something, or if it's a natural deposit, if it's fast-moving water, the sand will be denser than if it's slow-moving water. It's not really controlled by stress history. And what I mean by stress history is if you know maximum pass pressure and OCR, or alternatively maximum pass pressure and the current vertical effective stress or something like that, that information alone is not really adequate to tell you what the density of the sand is. It could have 30% relative density, it could have 85% relative density. It just depends on how dense it was when it was deposited. On the other hand, density of clay really is kind of controlled by its stress history. If you know where the normal consolidation line is in E natural log sigma V prime space, for example, that's the one with the slope of C sub C. If you know that line and you know sigma V prime and OCR, for example, you know exactly the path that the clay went through to get there, right? So it is sensitive to stress history. Okay, another thing about the critical state lines. In E natural log P prime space, the critical state line for sand is curved, but for clay, it's a straight line. So this plot right here is E ln P prime, and you can see that sand has a straight line. Clay has a straight line. Sand curves down like this. So if you took that equation that Malcolm Bolton gave us for the critical state line, in EP prime space, it curves this direction, but if you transform it into a log scale, it curves the other direction, right? So it's not a straight line, it's curved. And of course, clay, if you plot it in EP prime space, is also curved in this direction, but straight line in E ln P prime space. It just so happens that this critical state line for clay tends to be parallel to the isotropic consolidation line. So maybe you would have a normal consolidation line here, right? And these are two straight and parallel lines. And that has implications for the way that the shear strength of clay normalizes with effective stress and OCR, and that'll be a separate lecture. All right, the last thing is that sand does not really have a well-defined normal consolidation line. We don't do consolidation tests on sand, for example, right? We don't try and find C sub C and C sub R because it's not very well defined. It would be different for dense sand than for loose sand and so forth. And since sand is not really, the density of sand is not really controlled by its stress history, it's not as important to understand the isotropic consolidation line or normal consolidation line behavior. Whereas we do know that it has this critical state behavior, right? And then for clay, they're parallel. So here I've given it a slope lambda. You might be wondering, why isn't the slope C sub C? We know that E versus log sigma V prime, that slope is C sub C. Well, the only reason is that now we're plotting natural log of P prime on the x-axis, right? So it's not C sub C. The slope is going to be different. First, because it's a natural log instead of a log base 10. And second, because we're plotting ln of P prime instead of ln of sigma V prime. And so there would be a K-naught effect there, too, that would go into P prime. But these two are related by just a scalar factor, right? Lambda is equal to some scalar multiple of C sub C. All right, so those are the differences between sands and clays.